remember to follow the recommended safety practices. Use protective clothing and equipment, such as a welding hood, flame retardant clothing, and welding gloves. Take fire and explosion prevention measures, such as keeping a neat and clean workspace with no flammable materials nearby. Finally, be sure to use proper work area ventilation methods, such as this mobile-powered extraction system. Proper equipment setup is also necessary. Before welding, remember to prepare the area, set up the welding equipment, and prepare the metal to be welded. Preparing the area includes having a welding table, bench, or stand with a steel welding surface, and planning to be able to place weld coupons out of position. When setting up the area, be sure the area is properly ventilated, remove any flammable materials, and know where to find the closest fire extinguisher. Flash shields should be set up around your workspace. Practice weld coupons will be needed as well. Prepare them by removing any mill scale or corrosion with a wire brush or grinder. Also, the weld coupons will need to be prepared depending on the method of practice, such as running beads, overlapping beads, fillet welds, and open V-groove welds. When using the welding machine, follow these steps. Step 1. Ensure that the welding machine is compatible with FCAW. Step 2. Find the primary disconnect. Step 3. Set up the welding machine. Set the gun polarity, choose the appropriate liner material and contact tip for the gun based on the electrode diameter, and select the correct nozzle for the specific application. Step 4. Following the manufacturer's instructions, load both the wire feeder and the gun with the selected electrode. Step 5. Following the specifications set forth by the electrode manufacturer, connect the proper shielding gas for the application, if required. Step 6. Connect the clamp of the workpiece lead to the workpiece. Step 7. Turn on the welding machine. If necessary, purge the gun following the gun manufacturer's guidelines. Step 8. Following the manufacturer's recommendations, set the initial welding voltage and wire feed speed for the type and size of the electrode in use. Welding is impacted by a number of factors. Select each item to learn more. The welding voltage set at the power source regulates the arc length, which is the space between the electrode tip and the molten pool or base metal. Excessive voltage creates a longer arc, potentially causing the electrode to fuse to the tip, creating defects such as excessive porosity and spatter. Voltage and wire feed speed are interconnected and may require adjustments to achieve the desired weld. It's essential to set the voltage so that the arc length is slightly above the base metal surface. Welding amperage is controlled by the wire feed speed control on a standard power source after the welder sets the initial recommended setting. The power source ensures the required amperage for melting the electrode while preserving the selected welding voltage. Increasing the wire feed speed leads to higher amperage, deposition rate, heat, penetration, and bead size. Reducing the wire feed speed has the opposite effect. Some constant voltage welding machines for FCAW offer amperage modifications, such as slope or induction adjustments. This enables the precise short-circuiting current to be determined for specific welding needs and electrode specifications. Pulse transfer welding machines enable peak and background current adjustments to match different welding requirements. In some instances, a voltage sensing wire feeder pairs with a constant current welding machine, allowing current adjustment while the wire feed speed adapts to maintain the correct arc voltage at the electrode tip. However, some codes may prohibit the use of constant current machines for FCAW. Weld travel speed refers to how fast the electrode tip moves across the base metal during welding, typically measured in inches per minute, IPM, or a metric equivalent. The travel speed significantly impacts penetration and bead size. Slower travel speeds result in larger beads with deeper penetration until the arc no longer contacts the base metal at the front of the puddle, potentially causing fusion issues. Conversely, faster travel speeds create smaller beads with reduced penetration. Ideally, welding parameters should be fine-tuned to maintain optimal electrode performance. Gun position in FCAW also impacts weld penetration, voltage, and travel speed. The gun travel angle is an angle less than 90 degrees between the electrode axis and a line perpendicular to the weld axis. The three main types of travel angles are the neutral angle, push angle, and drag angle. When the gun travel angle is a neutral angle, the electrode of the gun is perpendicular to the welding surface, and the weld penetration is moderate in this position. A push angle, which is typically used for thin materials, is created when the welding gun is tilted back and the electrode tip and shielding gas move ahead of the weld bead. This type of travel angle creates a wider weld bead with less penetration. A drag angle is created when the welding gun is tilted forward and the electrode tip and shielding gas move back toward the weld bead. This type of travel angle creates a higher and narrower weld bead with maximum penetration. The gun work angle is an angle less than 90 degrees between a line perpendicular to the workpiece surface and a plane determined by the electrode and weld axes. Electrode extension is the portion of the electrode extending beyond the welding gun's contact tip. Modifying the extension affects the welding current for less conductive metal electrodes by altering the degree of preheating due to the electrode's resistance to current flow. As the extension lengthens, the preheating of the electrode also increases. Stick out refers to the length between the gas or insulating nozzle and the electrode's tip. Standoff distance is the measurement from the gas nozzle or insulating nozzle to the workpiece. During FCAW, spatter can accumulate on the gas nozzle and contact tip. Neglecting to clean the gas nozzle can impede shielding gas flow and lead to weld porosity. Additionally, when making out-of-position welds, spatter buildup in the nozzle can cause a short circuit, resulting in the nozzle sticking to the workpiece. To prevent these issues, clean the gas nozzle using appropriate tools like a reamer or round file, and consider applying an anti-spatter compound that is compatible with the welding equipment. When welding with FCAW equipment, it's important to know how to create stringer beads, weave beads, weld restarts, weld terminations, and overlapping beads. Select each item to learn more. Stringer beads are created by moving the electrode in a straight line without any side-to-side motion. Follow these steps to run stringer beads. Step 1. Hold the gun at the desired travel angle. Drag or push with the electrode tip directly over the point where the weld is to begin and pull the gun trigger. Step 2. Hold the arc in place until the weld puddle begins to form. Step 3. Slowly advance the arc while maintaining the gun angle. Stay in the leading edge of the puddle to prevent incomplete fusion. Step 4. Continue to weld until a bead about 2 to 6 inches long is formed. Step 5. Stop. Raise the gun to a neutral or 0-degree travel angle. Pause until the crater is filled, and then release the trigger. Step 6. Inspect the bead for straightness, a uniform appearance of the bead face, a smooth, flat transition with complete fusion at the toes, and undercut less than 1/32 of an inch deep or 10% of the base metal thickness. Also, check to ensure that there is no excessive porosity, overlap, pinholes, inclusions, craters, or cracks. Weave beads are created by moving the electrode from side to side. The width of a weave bead depends on the extent of this side-to-side movement. Follow these steps to run weave beads. Step 1. Hold the gun at the desired travel angle with the electrode tip directly over the point where the weld is to begin. Step 2. Pull the gun trigger. Step 3. Hold the arc in place until the weld puddle begins to form. Step 4. Slowly advance the arc in a weaving motion while maintaining the gun angle, as shown here. Step 5. Continue to weld until a bead about 2 to 6 inches long is formed. Step 6. Stop. Raise the gun to a neutral travel angle, pause until the crater is filled, and then release the trigger. Step 7. Inspect the bead for straightness, a uniform appearance on the bead face, a smooth flat transition with complete penetration and fusion at the toes, and undercut less than 1/32 of an inch deep or 10% of the base metal thickness. Check for excessive porosity. Pores should be no larger than 3/32 of an inch or 2.38 millimeters. Finally, ensure that there is no overlap, pinholes, inclusions, craters, or cracks. A restart is the point where a new weld connects to and continues the bead of a previous weld. Restarts are important because an improperly made restart creates a weld discontinuity. One advantage of the semi-automatic FCAW process is that restarts can be minimized. If a restart must be made, make sure it blends smoothly with the previous weld. The technique for making a restart is the same for both stringer and weave beads. Follow these steps to perform a restart. Step 1. With the weld clean, hold the gun at the proper travel angle while restarting the arc directly over the center of the crater. Step 2. Pull the gun trigger. Step 3. Move the electrode tip over the crater in a small circular motion to fill the crater with a molten puddle. Step 4. Move to the leading edge of the puddle. As soon as the puddle fills the crater, continue the stringer or weave bead pattern being used. Step 5. Inspect the restart. A properly made restart will blend into the bead, making it hard to detect. If the restart has undercut, not enough time was spent in the crater to fill it. If the restart has a lump, it was overfilled. A weld termination, occurring at the end of a weld, typically results in a crater, and welding codes mandate that the crater must be completely filled to the full cross-section of the weld. This can be challenging, especially at the plate's edge, where heat accumulates, making crater filling more difficult. Follow these steps to make a weld termination. Step 1. Start to bring the gun up to a 0-degree travel angle and slow the forward travel as the end of the weld is approached. Step 2. Stop the forward movement about 1/8 of an inch from the end of the plate. At a 0-degree travel angle, crater is filled. Backpull, depending upon the size of the crater, is completely filled. Step 3. Filled to the full cross-section of the weld. Overlapping beads are created by laying down consecutive weld beads in parallel, causing them to overlap and create a flat surface, also known as padding. This technique and weave beads to build up a surface and for multi-pass welding, relatively flat surface, whereas improperly overlapped beads will have an uneven surface exhibiting excessive buildup, undercut, and underfill. Stringer or weave beads, using a specific diameter flux cord electrode and, if necessary, the proper shielding gas. Deal. Step 2. Weld a stringer or weave bead along one edge at a 0-degree work angle. Step 3. Clean the weld. Step 4. Position the gun at a work angle of 10 to 15 degrees toward the side of the previous bead to get proper tie-in and pull the trigger.